Well, so today we will just revise the topics we have discussed throughout the lecture series of lectures I have given on vector calculus. Yeah, so this is the book, as I already mentioned, Spigel, Vector Analysis. Lots of examples are there. You can uh, practice all the problems, and the major things we have discussed, or major concept we have introduced uh, uh, in this lecture series: vector valued functions and its differentiability. This is the concept, and I think by now you know that it is basically extension of the concept of differentiability for a function of single variable or function of scalar function of two variables, three variables, etc. So if we look at the differentiation component wise, okay, so only thing is that the function involved in the process is a vector function, but the components are individually scalars. So therefore we translated the idea conveniently. Then we introduce line integral, any integral which is evaluated along a line, basically space curve or portion of a space curve. It may be closed or it may be open. Okay, so that is called line integral. Okay, so one way to define line integral is to evaluate the function at a particular point, and then you consider a very tiny line element there and take its length and multiply this with the component, tangential component of the vector at that point. Then you will get your element, integration element, and then you take the sum over all such elements. You will get line integral. And finally, of course, we have to take the limit. And if that limit exists uniquely, it is called the line integral. And line integral along the curves joining any 2 points for a particular vector function or a vector field may depend on the path under consideration joining the points, or may not depend. Okay, so it may be independent of the path joining the points in space, 2 points in space, or it may depend on the curve joining the points. And if it depends on the curve joining the points A and 2, the corresponding vector field is called non-conservative. And if it is independent of the path joining 2 points for any 2 points, then then it is called conservative vector field. Similarly, we have introduced the concept of surface integral. Here region of integration is the surface in 3-dimensional space, and within that space and within that region a vector function is defined. Vector function or scalar function is defined. Surface integral can be defined using a vector as well as scalar function. So we have defined surface integral using similar approach. Then we have defined vector integral, gradient, curl, divergence, and then Green's theorem in a plane, Stokes theorem, Gauss divergence theorem, and their application means some problems. So these are the things we have discussed in this class. Vector valued function, you already know what is this. It may depend on a single scalar variable, or it may depend on on 2 scalar variables or more than 2 scalar variables. Here some of the examples I have listed. So vector derivative, ordinary derivative of vector function is defined using this formula. It is quite similar to the one we have used for defining derivative for a function of single variable. Okay, for a scalar function of single variable. If you look at the components, these are nothing but ordinary derivatives. So we have to take care the components carefully, then we will get the vector differentiation of a vector function with respect to some scalar variable. Now, if this vector is a function of more than one variables, we can similarly introduce the concept of partial derivative. Okay, we will differentiate the function with respect to a single variable. Sometimes if the variables are x, y, z, then sometimes we will differentiate it with respect to x only. We will consider the change in x and the respective change in the vector, and we will consider the differentiation accordingly, partial differentiation accordingly. And here's some of the basic formula.
Hello.
Yes.
Sir, around 150 members are there in the wrong meeting, sir.
So same problem every day.
And it also has the same link, sir.
No, I asked you to not to start the meeting actually. So if you start the meeting, so several people are starting the meeting, and
Someone
then
started.
someone of you started actually. I joined that link. Okay, already there was a meeting. So they are not able to join this meeting only, this meeting?
Yes, sir.
Yes, sir. They got another meeting exactly.
So ask them to join the meeting where I am visible.
I think so, sir. They are joining to the same link, but they are being directed to another meeting, not in this one.
No, this is typical MS Teams problem. Actually, better not to start any
If
meeting.
they join through the browser, then this problem will be resolved. I think this is the problem of MS Team app.
Yes, sir.
So you drop a.
Like they are joining from link, they can join from the channel directly.
Yeah, so I have scheduled the meeting in the general channel today.
Yes, sir. We can join through calendar also.
Yeah. So drop a message there and ask them to join. Otherwise, what to do? Anyway, so these are some of the basic formula. So these are self-explanatory, and we have used this formula several times. And continuity is also defined similarly, and it can be proved that if the components are individually continuous, then the vector function is also continuous at a particular value of t. So these are the definition of partial derivatives, and we have similar kind of formula for partial derivatives as well when we have a vector function of two variables. Well, so scalar field, vector field, these are the things we have. These are two concepts we have introduced. Vector scalar field means it is basically a region of space where a scalar function is uniquely defined. That means if you take a particular point from that region, and at that point you can calculate the value of the function uniquely. Okay, so we have scalar function, and once we have a scalar function, say x square plus y square plus z square, or x square plus 2xy, something like that, or y square equal to 4yz, something like that, plus 4yz, something like that, then that will help us to define level surfaces by considering the equations of the form phi is equal to constant. For example, if phi is equal to x square plus y square plus z square, then phi equal to constant, positive constant of course, because x square plus y square plus z square cannot be negative if x, y, z are real variables. So we are considering real variables. Okay, so that will give us spheres, concentric spheres. If you change the value of the constant, you will get concentric spheres, and each sphere is a isophi surface or level surface defined by this scalar function phi. Okay, similarly we can define vector field. If a region of in a region of space a vector function is uniquely defined at each and every point. If we can define a vector function uniquely, then the region it will be said to be a vector field together with the defined by the function f. And we then introduce the concept of vector gradient of a scalar field. Suppose we have a scalar function phi x, y, z, and then at a particular point the gradient of a vector means the maximum rate of change of uh, gradient of a vector at a particular point means through that point a unique level surface will pass, and at that point at that point, gradient of phi will give us the maximum rate of change of phi together with its direction. Maximum rate of change of phi together with its direction. And we know that after all the discussions, we know that gradient of phi at a calculated at a particular point will give us a normal vector to the level surface passing through that point. Okay, so we have derived the thing, and then we introduce the concept of directional derivative. So what is the directional derivative? The component of gradient of phi in a particular direction. So a dot grad phi. Grad phi is the gradient of phi at a particular point. And now if we take the component of grad phi in a particular direction given by a cap is called the directional derivative of phi at the point P in the direction of A, and it is normally denoted by the symbol del phi del S. And the operator A dot grad, A is some unit vector, dot grad is called the directional differentiator, and this symbol is called nabla. Well, some of the examples we already discussed, and then we went to vector integration, and it had been defined naturally. Okay, so first we introduce the concept of improper integration, indefinite integration of a vector function A. Okay, so there is a typo, it will be R. Anyway, I will correct it. No, it is fine actually. So am I not audible to you? Hello?
Now it's okay.
You are audible. Sir, you are audible.
Now volume increased little bit.
Yes, sir.
Yes, sir.
It's already good, sir.
No, sir, it was fine already.
Okay, so so this is the definition. So as antiderivative, actually integration has been defined here as antiderivative together with a vector arbitrary vector constant over here. If a is equal to ddu of ru, then integration of au is equal to ru plus c. C is some arbitrary vector independent of u. And we have mentioned that if we integrate component wise, we will get the same result. And then we mentioned the definition of definite integration in a similar manner as we have done for a function of single variable. So basically, if the indefinite integration of au is ru, then a to b au du is equal to rb minus rn. So this is how we will substitute the limits, and then line integral. So any integral which is evaluated along a curve, space curve, finite portion of the space curve, or along a curve, basically it is called a line integral. It may be closed or it may be open. Now if a is a vector function, then how we have defined here, region of integration is a portion of line or space curve. So we will divide the region into finite parts by introducing some points, between the initial and terminal points on the curve, and that will divide the curve into different parts, and from each part we will take a point. Okay, not necessarily it should be initial point or final point. It can be in fact any point xp within that interval. We have shown it over here. Okay, so then we will calculate the vector function associated with this. At this point we will get a vector, and then we will take the dot product of that vector with the length of this segment. Okay, so delta r, we have denoted it by delta r. So a dot delta r, this is our integration element, and we repeat the same work for each of the elements on this curve and form the sum and finally take the limit. If this limit exists, it is called the line integral. Okay, so this is how we have defined line integral, and then we have solved some problems. This is the Cartesian form of the line integral. A dot dr And in particular, if A is the force field defined in a particular region, then this line integral will give us the work done by the force in moving a particle from the point A to the point B. So depending on the nature of this vector, uh, the
Excuse
physical
me, sir.
yes,
Sir,
physical
sorry to interrupt, but many people are not able to join. Sir, can you please go to the settings and change the settings when attendees may come? Can you do it like always? Change it to always.
Acha, so just let me do it.
Yes.
So from where I can
show device emitter. Yes.
meeting details, meeting options, right? Everyone I have. So what else I can do? I have allowed everyone. Means they can use their Gmail to join the meeting. So I think
Sir, allow only institute mail.
no, then only institute mail they have to use. Using Gmail
Sir,
also they can
in spite of using the same link, we were landing into someone else's meeting.
Yes, sir, and there are 150 students in that meeting.
Acha, so
Yes, sir.
whoever started that meeting can he or she end the meeting?
So they can
Sir, the
directly
same
join
meeting link.
calendar or the channel.
Acha, so let me just will I be able to stop that meeting? Then I have to join there itself. 2 meetings now.
So don't do this. Don't do this.
Yes, sir. You stay in the same meeting, sir. Otherwise, it will be problem for us.
Yes, sir.
Yeah.
It
Yeah,
will be
so
problem
ask
for
the
us if we join
students.
another meeting.
Yeah, so whoever has started that meeting,
After we will
probably
ask them to stop.
that student has the has the
Sir, I think there's also an option where there will be a time when they can join. So can you please change it to always?
which one?
Sir, I think in the settings there's also an option like they're saying that there's an option that there's a time when they can join. So if you change
Just
it to like always, you can join. Something like that.
where? So all reactions bypass the load. I don't see
Sir,
it.
in the second one, I think it's always.
Yes, sir.
Yes, sir. The second one, can you change it to yes?
Yes, sir.
Second.
It
Which
is
one?
already
Always let caller
Yes.
bypass.
Yes, sir.
Always let.
That one.
it is always yes, and sir cannot do anything else.
It is always yes. Yeah. It is always yes. So ask them to join using their Gmail. If this is not, and yeah, so by looking at the
Directly
time
join from the
they
channel.
can, yes, 32. So the meeting which is going on for 32, 33 minutes, around 33 minutes, that meeting they can join. So whenever they will enter this MS Teams, they will see that there are several meetings going on. Okay, so but they can select the right meeting by looking at this time.
So now 3 meeting going on.
So I don't know what they are doing.
Yes, sir. The main meeting is not visible only. That's the main problem, sir.
So 33 minutes, this is not visible?
No, sir. When we are trying to join, even after clicking the calendar, we are getting redirect to the other meeting. Means that where all are waiting for the class. That one, sir.
Sir, actually that is the problem for MSTV. In the previous classes, I have faced that problem. But you know, if I joined through the browser, that problem automatically got resolved.
So then ask them to join through the browser actually. So in the group you drop a, so I am also dropping a message here.
Yes, sir. In the browser by mail ID and password. In the browser, they can join from their mail ID and password.
Yes, sir. They can join through that.
Please join using the MS Team browser, no?
Any browser? Yes, sir.
I don't know. This is probably MS Teams issue.
Yes, sir. This is the problem of MS Team.
Initial 4-5 classes and we did not have any problem.
Software cannot understand why to send.
Yeah, and they can also you can also join
channel
using your Gmail. Same technical problem.
So also share the link once.
Acha, so where can I get the link?
From the meeting details.
Achha.
Meeting details. Yes, sir. So copy link.
So now what is the attendance? So it is around 180, so 179. So anyway, let me continue so they can.
Sir, in the previous part, there was XP. XP is a point in the previous page.
Yes, yes. It is a point within this arc, this general arc. So basic idea is similar. You might understand at this moment. So for a surface integral, region of integration will be a surface in three-dimensional space. Okay, having a boundary. Okay, it may not be boundary. It can be surface can be closed as well as open. So for surface integral, and what we will do, we will basically divide the surface into different parts. And from each part we will take a point. So here PP is the point. You see P suffix P, that is the point. And at this point we take a normal. So the normal is chosen, user chosen rather. Okay, either we can choose it inward or outward. It depends on the user. And accordingly we'll get the line integral, a surface integral. Okay. So at this point we will calculate the value of the function, because at each and every point this vector function is defined, and then we'll take the normal component of it. We'll get a number, and then that number is multiplied by this area. Okay, so that is our integration element, and we repeat this for each and every surface element and take the sum and finally take the limit. Okay, so if the limit exists, we will say that this is the double integral, surface integral of this vector function A. This is one kind of surface integral of A over the surface S. And this ds, this surface element, to evaluate this or to change this in Cartesian form, we take the projection of this on xy plane. on xy plane. If it is allowed, for the projection to be allowed, what we have mentioned that it should be 1 to 1. Okay, if it is more than 1 to 1, that means 2 to 1 or many to 1, then we will not consider that projection. Okay, so someone is okay, so there is a little bit more enhancement in the participants. Let's see. I can see your message here but cannot see you. Look at the time of the meeting and join the meeting, which is going on for about 40 minutes. Okay, so if this limit exists, then it is called the surface integral, and for evaluating the surface integral, it is necessary to convert this to a using a projection, appropriate projection of this on the coordinate planes. Okay, so while taking the projection, we have to be little bit careful. So that projection is we have to check whether the projection is 1 to 1 or not. Okay, so I will discuss some of the problems today. And surface integral can also be defined using a scalar function as well. Definition is similar, only the thing is that this function is scalar. Okay, otherwise everything else is similar. In this case, if you evaluate, you will get a scalar number, you will get a number, and in this case also, the way we have defined surface integral, you will also get a number, but interpretation will be different. For example, for this surface integral, if we take phi is equal to 1, so we'll get the area of the surface under consideration. Well, so now yes.
Sir, if we are taking the projection of the plane along YZ or suppose XZ plane, then accordingly that n dot k value will get changed, na?
Yeah, you have to take the dot product of n with I or j in that case, depending on the plane.
Perpendicular to the projection of plane.
Yes, you have to basically determine the angle between the surface element and the projection plane of projection. Yeah.
Yes, sir.
Cos theta. And if the surface equation of the surface is given in this form, z is equal to fxy, then this will take n dot k will take a particular form which has been mentioned over here, delta f by mod of delta f, that will give us the unit vector, unit normal vector dot k. We have to take the absolute value of this, and it turns out that it takes this form for this particular surface, and we can evaluate the surface integral using this formula. Well, surface integrals and then volume integrals region once again changed. So how the region here, region is a portion of space. Okay, and that portion of space is divided into, once again, different tiny parts, each of which is a rectangular parallelepiped having dimensions delta xk, delta yk, delta zk. So this is the small region, and from that region we will take a point, and at that point we will calculate the value of the vector function or scalar function, whatever is associated. Okay, so therefore for this kth element we get this integration element, and then we form the sum for all the elements, and finally we take the limit n tends to infinity. And if this limit exists uniquely, it is called the volume integral of the vector function A, and if the function is phi, the scalar function, we call it the volume integral of phi over the volume B. Well, then we have the Green's theorem in plane, which is within a plane, which basically connects a line integral over a closed regular curve, closed simple regular curve with a double integral, So this is the line integral over the closed curve C, and this line integral is taken in positive sense. That means we have to take the sense of description of C in anti-clockwise direction. Okay, so then this relation will hold between the line integral and the double integral. Or you can, in particular, you can call it as a surface integral, although surface is a portion of plane. Well, so we have discussed the proof of it, and then this is the vector form. Same thing is written in vector form in this way. Then we have verified Green's theorem for this particular example. And today I will discuss, so how many of you could join now? So now it is 200. So slight increment. Okay, so verify Green's theorem in the plane for this particular line integral x squared dx plus xy dy, where gamma over this curve gamma, closed curve gamma, gamma is the square in the xy plane bounded by x equal to 0, x equal to a, y equal to 0, y equal to a. This is not q, this is a. Okay, so you check the Green's theorem. X squared dx, xy dy. Okay. So this is our gamma, x squared dx plus xy dy. And what is gamma? Gamma is the curve, boundary of this curve 0, x equal to a, y equal to 0, y equal to a. Okay, so note that for this case we have to consider sense of description of the boundary curve of this square in anti-clockwise sense. Yeah. So let us first draw the region of integration. So this is the square, x equal to a, and this is y equal to a, and r is this, and p is equal to x square, q is equal to xy. Okay, so first we will basically find this del q del x minus del p del y. Del q del x is equal to y and del p del y equal to 0. So according to Green's theorem, we should get what? Gamma x square dx plus xy dy equal to, we should get this r y dx dy, right? According to Green's theorem. So according to Green's theorem, we should get this. Now we have to check whether we indeed are getting this or not. And sense of description of gamma is this, anti-clockwise. Okay, so you calculate this. This is your O, A, B, C. So this is your gamma x square dx plus xy dy. So along OA, x will vary from 0 to a, and x square, and what is your y? Y is equal to 0. Note that along OA, y is equal to 0. So therefore x square dx This is the line integration along OA, or should I write it explicitly? Achha, so let me just write it as OA. You have something, and then AB you have this line integral, and then on BC plus CO. We have to divide the integral into 4 parts. So on OA, what we have? On OA, we have y equal to 0 and dy automatically is equal to 0, and x will vary from this. On
0 to
A, on AB.
So now we can join, sir, after trying for 30 minutes.
Acha, so so I am just helpless. I don't know. This technical glitch.
Sir, actually, sir, with the same meeting link, 2 people are creating the meeting. The meeting that is starting later, we are joining in that every day. Actually, that is the problem.
Actually, who have started the meeting, so he has the option to end the meeting.
End the meeting.
They can, if they can stop the meeting, then one can
and join the proper meeting. So that meeting going on.
Yes.
So the one who is starting the meeting is leaving the meeting without ending it, sir.
Yeah. So.
But there should be one meeting going on. Why he is starting another
With the
meeting?
same link, how can it be possible, sir? Every day, many members are facing problems, sir.
I don't know whether this is a technique. I think initially we did not have any problem, so it started later on.
Yes, sir.
Is it MS Teams? So are you facing the similar problem with other teachers?
No, sir. Only for this.
No, sir. Only this class, sir.
Because remaining classes are only for the individual sections, sir. This is for more than one section.
Okay. Now many students are joining. 243.
Trying from 40 minutes, we got now joined.
Yes, sir. Because the meeting that has started later has ended, so we can join now, sir.
Before the third time finding the link. Now I got it.
Okay, so let us wait for 5 minutes, or then I will start.
Actually, the ones joining now have joined as a guest.
Yeah, anyway, so all are allowed now. I have allowed everyone. Anyone can join actually.
So we had to copy the link, paste it in Chrome, and then we were allowed to enter as guests. Then only we are able to see you. Otherwise, with our institute IDs, we went into another meeting.
Okay, so then, yeah, so as I mentioned in the chat box that you have to use, some of your friends basically suggested that you have to use the browser. Then it is working. Yeah, attendance will not be a problem. So, yeah, my intention is to discuss the thing so that you can learn. Yeah, so now I can see, yeah, 254. Yeah, so this is the line integral. So we have to evaluate the line integral on individual parts where we have some special information. For example, on OA, we have the information that y is equal to 0. So that we can use. And then on AB, what we have x is equal to a. Therefore, dx will be equal to 0. On AB, x is equal to a, that is constant. That means x will not vary. So dx, this is equal to 0. So that you can use. On BC, you have also some information. On BC, y is equal to b, y is equal to a, and dy equal to 0. Okay, and x will vary from a to 0. And on CA, CO, x is equal to 0, and dx is also equal to 0. So therefore, if we use all the information, then in this case we will get 0 to a x square dx, and on AB what we have, x is equal to a, and x is equal to a means dy is equal to, so plus basically 0 to a, x is equal to a, dx is equal to 0, therefore a y dy, and BC, on BC what we have, on BC integration will be from a to 0, note that BC a to 0, and we have on BC y is equal to a, dy is equal to 0, dy equal to 0, dy is equal to 0, that means second term will not be there, x square dx, and on CO what we have, on CO we have x is equal to 0, dx equal to 0, so first term is equal to 0, so everything is equal to 0. Now you see this is cancelled, plus 0, this will not contribute, and this one is the only one which will survive this term, so a square by 2, so a cube by 2, this is the line integral. So what is the a cube by 2? Yeah, right. Now we have to find the double integral right hand side. Right hand side, this is equal to the region R del q del x minus del p del y dx dy, and this is nothing but x is equal to 0 to a, y is equal to 0 to a, and we got y d, this is dx and dy. So here we get y square by 2, that means a square by 2, so in fact you will get a cube by 2. So therefore left hand side is equal to right hand side. So Green's theorem is verified. Theorem is verified. Okay, so therefore whatever was the claim of Green's theorem, that has been verified by the actual calculation. We have evaluated both the line integral as well as the surface integral or double integral in this case. Well, so let us go ahead. So these are similar problems. Just you have to understand the region of integration, and then you have to choose the limits appropriately. That is the key. And px qx is very these are obvious actually. The function which is multiplied with this dx is p, and which is multiplied with dy is q, and then you go ahead and calculate, you will get the result. Well, so now the divergence, we have introduced the concept of divergence. So what is that? So to define divergence, we define the normal flux of a vector across a surface S. So how did we define that? So if delta S is a surface, this delta S is a surface defined inside a vector field. Vector field means at each and every point on that region a vector function is uniquely defined. Then if P is a point on this surface delta S, then at that point we have this vector you can calculate. Let us suppose this is the vector, and then you take the normal component of this vector along a chosen normal. It can be this side or the other side. Okay, you take this normal component of this vector, and then you will get a number, and you multiply that number with the area of this surface. So therefore what you will get, you will also get a number, scalar number, and that scalar number is called the flux of the vector f across the surface delta S. And this is done for a surface element, tiny surface element. And if you do it for a finite surface area S, then we have to integrate. This is the element, and if we do it for an open surface or a closed surface, if you take the sum and take the limit, we will get the surface integral, and that surface integral is called the gives us the normal flux across the surface S, across the surface S, normal flux of F across the surface S. Now let us consider a closed surface delta S, this, which is enclosing a volume delta V. Okay, therefore this one, so what this one will give us, this quantity, this surface integral will give us the normal, and you take the normal flux of F across the closed surface delta S, and within delta S there is a point P, okay, at which we are interested to define the concept of divergence. So you have a point P inside, and then which is enclosing, that point is enclosed by a closed surface delta S, and we are calculating the normal flux across the surface delta S, and this normal is taken outward. This normal N is taken outward. Then this is the normal flux of F across the surface delta S. Then what we are doing? Then we are calculating the normal flux per unit volume by this quantity. Delta V is the volume of that region. So delta 1 by delta V normal flux. So this is the normal flux of F across delta S per unit volume. Then we are taking the limit delta V tending to 0. If this limit, okay, so we are taking the limit in a specific manner. So delta V is made or tend to 0 in such a way that the point considered inside it always remain inside. Okay, if this limit exists uniquely, this is called the divergence of F at a particular point P. In particular, if F is the velocity field associated with a fluid system, then this quantity will give us the amount of fluid which is if this is positive rather, and it can be also shown that it is independent of the choice of the shape of delta S and delta V. Okay, so if this limit exists, it can be proved mathematically that this limit is independent of delta S as well as delta V. Okay, so therefore we can define this quantity at a point uniquely. If this number is positive, divergence of F can be calculated using this Cartesian formula, derivation of which we have not discussed, but yeah, so we can in principle prove it. Okay, so you will get a number. If that number is positive, then and F is the velocity field, we can understand that some amount of fluid is coming out of the region, coming out of the point P under consideration if it is positive, and in that case P is called a source, and if it is negative, that means fluid is leaving the system through that point. The point is called sink in this case, and if the divergence of F is equal to 0, then there is no net fluid movement through that point. That means the amount of fluid, if you consider a tiny closed surface around that point, the amount of fluid which is entering the tiny volume, that is equal to the amount of fluid which is leaving the tiny volume. Okay, so therefore there is no net movement, net accumulation of fluid or leaving the fluid from the system through that point. Okay, so then we defined curl. How did we define curl? So suppose you consider a closed curve C, which is oriented. Oriented means there is a specific arrow direction, and with this, which is forming a boundary of a surface delta S. surface capital delta S in space. And on that surface you consider a particular point P, and around that point you consider a very small surface element delta S. Very small surface element delta S. And the direction of this unit normal to the surface element delta S is taken to be positive with respect to the sense of description of this boundary curve C. And how to determine the positive direction of the normal with respect to the sense of description of this, I have already mentioned that the observer has to move along the curve C following this arrow direction, and during that time the surface area under consideration will be in the left hand side of the observer, and the head of the observer will be oriented towards this normal. If that happens, then this normal is called the positive with respect to the orientation of the or sense of description of the curve C. And then we can calculate the circulation of F along this closed curve. Okay, this is basically a line integral, and it is evaluated with the specified sense of description of the C, of the curve C. And then the average circulation per unit area is given by this 1 by delta S F dot dr. This circulation, average circulation is this. And then what we do, we consider the limit delta S tends to 0, and once again, while considering the limit delta S tending to 0, we'll keep the point P under consideration always inside the region delta S, inside the tiny surface delta S, which is enclosed by the curve C. And it can be shown that this quantity, if this limit exists, it depends only on the choice of the normal vector n. It does not depend on the shape of the surface delta S, Okay, only it depends on this quantity depends on the choice of the normal n. Then we are defining a vector called curl F, whose dot product with the normal vector considered at that point P is this. Then, so we mentioned that the curl of F is equal to this. It can be evaluated using this formula, and therefore, if I give you a vector F as a function of x, y, z, three scalar variables, then curl of F you can immediately calculate using this formula, and you will get a vector. And then once you know the vector and you take a point inside the vector field, you can calculate the constant vector. Okay, you just put the point in that curl F, in the vector function curl F, and then you choose any unit normal at that passing through that point and take the dot product of that vector with unit normal. You will get a number. It may be positive, negative, or 0. If the number is positive, then the vector field will rotate in anti-clockwise sense about the chosen normal n, and if it is negative, the vector field will rotate in clockwise sense about the unit normal n. Okay, if it is 0, there is no rotation about the chosen normal. So these are the physical interpretation. And then we have the divergence theorem, which connects, this divergence theorem connects surface integral with the volume integral. Note that this surface has to be closed one. Then only we can apply this divergence theorem. If we choose a closed surface inside a vector field, that means region of space where a vector function is uniquely defined, and the volume of that region under consideration is V, which is enclosed by these closed surfaces, then divergence of F, see nabla dot F means divergence of F dV. Volume integral of this quantity is equal to the surface integral of F given by this n dot F ds over the closed surfaces. I repeat that it is always applicable for closed surfaces. Okay, and note that this unit normal always we have to take outward unit normal. if you do not take outward unit normal to a closed surface, then there will be a sign problem. Okay, you cannot balance these two integrals in that case, and this problem we already discussed. And next we have the last topic, Stokes theorem. It connects the line integral with the surface integral. Here the surface is open, it should have a boundary, otherwise we have to calculate the line integral. Okay, it should be open like hemisphere, portion of cylinder, something like that, or portion of paraboloid intersected by a plane. Okay, so the surface under consideration should be open in nature. It should have a boundary C, and this sense of description will be C will be such that this normal is positive with respect to the sense of description of C. And how to determine the positive normal to a surface, that I already discussed. The observer has to move along the curve C in such a way that the surface will always lie in the left hand side of the observer, and the head of the observer will be oriented towards the normal n. Then n is called the positive normal. So that way we have to determine the positive normal. And then if we calculate the line integral in the left hand side as well as the surface integral in the right hand side, they will be balanced. Okay, and these integrals are widely used in different branches of science and engineering. Okay, so this problem I already discussed, and today I will discuss couple of more problems, and here I have listed some of the vector identities which are frequently used. Okay, so curl of grad of some scalar function phi is always 0. Divergence of curl of a vector function is always 0, and here we have some other formula. Okay, no need to remember. So this one is frequently used in fluid dynamics and in electrodynamics. Probably this one is used. And in some of the cases these are also used. Yeah.
Sir, what is G represent here?
Vector, two uniform vector functions. You see, f and g be two uniform vector functions, and we are within the vector field and scalar field. Okay. Well, so let us first solve the problem number 1. Verify divergence theorem for this particular function, vector function taken over the first octant bounded by this cylinder. Note that we are in 3 dimensions now, y square plus z square equal to 9, and this plane x is equal to 2. Okay, so we have to calculate the surface integral as well as the volume integral. Okay, so let us just draw the region. So y square plus z square equal to 9 and x is equal to 2. Okay.
Excuse me, sir.
Yeah.
So we have another meeting from 10.
You have another meeting?
Yes, sir.
Then how to finish this problem? So when
Class tomorrow, sir.
tomorrow? Tomorrow at what time?
The scheduled time maths classes.
No, sir. Tomorrow we have our engineering mechanics class from 9 a.m.
So how we can be? So how engineering mechanics class can be there during that time, because it is scheduled mathematics class?
Actually, sir, as the summer vacation for faculties is going on, and that's why sir told us ki at that time sir will take the class to complete that syllabus.
And then when I can discuss? So do you need the discussion on these problems? So I thought that I will solve 4 problems.
Yes, sir.
Yes, sir.
Then tomorrow at what time will be available?
9 o'clock.
9 o'clock.
Sir, from 8 o'clock in the morning.
Yeah, it is fine for me if you are available.
No, sir. 8 o'clock. So
12.
9 o'clock.
No, sir. Tomorrow from 8 it will not be possible because we have yoga class.
Then latter part of the day.
Sir, in the evening tomorrow.